well, while it's still setting up, hi everyone, I'm Lucie, I'm a PhD student here in Leiden. And today I'm going to be talking about observations of very distant galaxies, so galaxies in the very early universe, hence the title of the presentation. But first, I'll hopefully Did it work? No. Oh, okay. So are you gonna? Yeah. Okay. Well then. Okay. So first, very quickly, a bit about myself, or like my background as an observer. So I grew up in London, and I became very interested in amateur astronomy. So if any of you have looked through an amateur telescope before, you might have seen something like this. Yeah. Yeah, so you might have seen an image like this before. So if you point your amateur telescope towards a local galaxy, you start to observe this kind of fuzzy cloud. Depending on how good your telescope is, you might start to see these kind of spiral arm structures. So I thought this was really cool. So then when I started my undergrad and my master's up in the University of Durham, I decided that I wanted to study physics and astronomy. And so then I was working on, I was able to use observations from the VLT, and I was observing again local galaxies, but as you can see it's much finer detail with much prettier images. And again, I thought this was really, really cool, but for my PhD I wanted to take this a step further. So I moved over to Leiden about 3 years ago, and I started my PhD looking at even more distant galaxies than this. So I'm now using some of the most powerful telescopes that we have available to us. But because I'm observing such distant galaxies, we're back to these kind of blurry blobs. But hopefully, throughout the course of this talk, I'm going to convince you that these are still really, really, really cool. Okay, so now if we go to the next slide, to put this talk in a bit of context, this is the kind of classic cosmic timeline that many of you have probably seen before. So we're pretty sure that the universe started something around 13.8 billion years ago. But it took a few 100 million years for light to first switch on in the universe, so for the first stars and the first galaxies to form. And then it took those galaxies another several billion years for them to really grow and evolve into the kind of galaxies that we see around us today. So galaxies like our own Milky Way, which have these beautiful kind of spiral structures, so this takes several billion years. And then what we're going to be, focusing on for this talk, the kind of cosmic era that we're looking at, is around here. So within the first 1 to 2 billion years after the Big Bang, so really when these very early galaxies are starting to grow and evolve into the kind of galaxies we typically see. Because we're looking at very distant galaxies, because we're looking at the very early universe, that means that we're basically looking at high redshift stuff. So this is a term that Jaeger introduced, but I'm going to quickly, hopefully, show a video to explain it in a bit more detail. So this is a spectrum of a galaxy. This means that we observe a galaxy and we see how much light it emits per wavelength or per colour. And we know that these typical galaxy spectra have very characteristic features. So for example, breaks where the amount of light that we receive suddenly drops off, and also these kind of sharp emission lines. I don't know if you can play the video again. But because the universe is expanding, this means that galaxies far from us are relative to us as observers moving away from us. And this means that the light gets stretched. This is that Doppler effect that Ian was talking about. The light gets shifted to longer and longer or redder and redder wavelengths. So those characteristic features get shifted basically to the red end of the spectrum. So this is what we mean by redshift. And it's important to just kind of keep in mind, the higher the redshift, the further away the galaxy we're observing is. And because light takes a finite amount of time to reach us, this means that we're essentially looking back in time into the early universe. And almost as soon as we kind of realised, or as soon as astronomers realised that we were within a galaxy, the Milky Way, that was just one of many, many galaxies in the universe, this kind of race began to try and break this record of what's the most distant galaxy that we can find. So this is the redshift frontier, or the highest redshift record-breaking race that kind of began around 1920s, 1930s. But I'm going to skip kind of the first 90 years of this history, because otherwise this talk would take an hour. And we're going to kind of skip straight to kind of what's happened over the past 10 years. So what was the picture like a decade ago, so in 2015? And in 2015, the record holder for the most distant galaxy that we've observed, or the highest redshift galaxy, was this galaxy EGSY8P7, it's this little blob here in the centre, and the ending of that name is because it's at a redshift of around 8.7. And what this means is that the light from this galaxy was emitted around 13.1 billion years ago, so something like 700 million years after the beginning of the universe, after the Big Bang. But because the universe is expanding, this is an effective distance of something like 30.5 billion light years away. And this was a discovery that was also had Leiden astronomers involved, so that's pretty exciting. But this is a very fast-moving field, so pretty much within the same year, or about a year later, astronomers discovered this other galaxy. So this is GNZ11. And from the data we had at the time, 10 years ago, we were pretty sure that it was at around a redshift of 11. So this is a jump from redshift 8.7 all the way up to redshift 11. So this would put it about 400 million years after the Big Bang. So already kind of reaching the limit of where we expect the first galaxies to have formed. But we weren't 100% sure, the data wasn't quite good enough to be certain, and it actually took another about 6 years for us to be certain what redshift it was. So this is when, in 2021, astronomers observed some of these kind of key characteristic features, which let us pinpoint its redshift exactly to 10.96. Now it's at this redshift of around 11 that we start to run into a problem. So at the time, in 2020s and earlier, our powerhouse for detecting these high redshift objects was the Hubble Space Telescope. And it runs into a problem at redshift 11, because like I said, the spectrum of galaxies shifts to red wavelengths, and this break, where below which we barely see anything, basically reaches the limit of what we can see with the Hubble Space Telescope at around a redshift of 11. So it was really not possible to observe higher redshift things at that time. So we really needed this guy, and luckily enough, the James Webb Space Telescope was launched on Christmas Day in 2021, and that opened up this much redder wavelength space, so the infrared spectrum that we had in the quiz. So it opens up much higher redshift observations than what was previously possible. So almost as soon as we got the first light observations from JWST, of course we blew this record out of the park with JWST 13. So this is at a redshift of 13.2. So this is just 400 million years after the Big Bang. But this record did not last very long. Like I said, it's a very fast-moving field. So about a year later, it was broken again, with also from the JADES survey, JWST 14. Now this was super exciting, not only because it's at such a high redshift, redshift 14.2, which is pretty exciting, but also because we managed to get follow-up observations, and we actually detected oxygen within this galaxy. So this is the most distant detection of oxygen ever, and that still remains. So this was a really exciting finding. This was led by a group also here in Leiden, so we gave ourselves a big pat on the back. We were very proud, very happy for like a couple of months. And then earlier this year, the record gets broken once again with this galaxy, MUMZ14. This stands for Mirage or Miracle. It's a bit of a funny name. This is still currently, unless I missed anything big today, the current record holder, so redshift 14.4. Now one thing you might have noticed with all these images that I've been showing, these really, really high redshift stuff, is they don't look like super impressive. But you can kind of see it here and here, like they're just like these tiny little blobs. Like it's very difficult to get a lot of information from these kind of observations. And the reason that is, we can press it again and play the video, is when we're observing galaxies in the local universe, so nearby galaxies, we get all this beautiful detail. We can resolve the galaxies in a lot of detail. But as we go to high redshift, things get further away, things get fainter and redder and smaller, so we can't really resolve it in that fine detail with our current telescopes. So we basically just get, very blurry blobs. So if we want to try and understand high redshift galaxies in kind of a greater amount of detail, we can't really do this at redshift 14 yet. So we need to kind of go, relax a little bit, go back a step, and go to slightly lower redshift. So now for the rest of the talk, I'm going to focus on slightly lower redshift, so around redshift 6 to 8. This is still only about 1 billion years after the Big Bang, so still talking about the very earliest galaxies and how they're evolving, but we're going to stick with slightly lower redshift rather than the redshift 14 stuff. And so what we want to try and understand is how these very, very early galaxies, which these kind of very small little blobs, how can they evolve into the kind of galaxies we see in our local neighbourhood. So a lot of galaxies that we observe, including the Milky Way and its surrounding neighbours, they look a bit like this. So they have these beautiful spiral structures, a bright nucleus at the centre, and then all these beautiful star-forming regions along the spiral arms. And what's actually happening with these galaxies is that they're rotating around their centre. And it's a very nice ordered rotation, everything's behaving very well. But our current theory for how these kind of galaxies form is that if we were to turn back the clock, we would expect that these kind of galaxies would actually form a bit like Lego, so with smaller galaxies colliding and merging together to form these more massive structures. So if we were to look earlier in the universe, a fair expectation would be that most galaxies we see would be kind of irregular shaped because they're colliding together. And indeed, when we look at our high redshift galaxies, where we can resolve slightly more detail, this kind of makes sense of what we're seeing. A lot of high redshift galaxies that we observe look very irregular, very clumpy, so we think, okay, this makes sense. Probably these are all, merging or interacting galaxies, and they're eventually going to form more massive spiral galaxies, kind of like what we see with the Milky Way. So I want you to bear this kind of picture and this idea in mind for what I'm going to talk about next. And so next I'm going to introduce my favourite galaxy, which is Rebels 25. So this galaxy was first discovered around 2007, but we weren't too sure what it was or what its redshift or how far away it was. Basically all we had was these kind of, blurred out blobs, but we were pretty sure it was a good candidate to be a very distant, very high redshift, massive galaxy. But we weren't too sure. So we went out and got more data, we observed it with the Hubble Space Telescope, and we go from having just one blob to now we've got what looks to be maybe 3 blobs. So we think, okay, maybe this is, a good candidate for a very high redshift merger, where, that kind of fits in with our picture of high redshift galaxies all being kind of clumpy things that are colliding together. But we still weren't too sure. It was still a candidate merger, and we weren't 100% sure what it was or how distant. So as always, we had to go out and get even more data. So we went and got even more data, and first we confirmed its distance. So we found that it was at a redshift of 7.3. This is around 13 billion years ago, so again, still within the first billion years after the Big Bang. But that still wasn't enough for us, so we went and got even more data. We observed even longer with ALMA, which is the radio telescope in Atacama Desert. And we obtained these very high quality follow-up observations of the gas within this galaxy, which I'm showing here on the left of the contours here. Now I understand that this still kind of looks like a blob, but I want to emphasize that this is really impressive for this redshift. This is really high resolution compared to what we normally get at such a high redshift. To try and convince you of this, it's kind of equivalent to being able to resolve a football field on the moon, except this galaxy is about 10 to the 17 times fainter. So 0.0001 times fainter than the light we can get from the moon. So really, really difficult, and therefore this was a really impressive data set to work with. And the first thing you might notice is this no longer looks clumpy. It looks like just one object, just one galaxy with kind of what looks like could be a disk. But ALMA doesn't just observe in the spatial dimension, we also get a third dimension, which is the velocity. And what this means is that for every area of this galaxy, we can see in what direction the gas is moving in and also how fast. And so when we follow this through with the analysis, we get a picture a bit like this. So for this picture, I want you to imagine that the red side of the galaxy is moving into the screen away from you, and the blue side is moving out the screen towards you. So you can see from this picture that basically this galaxy is rotating around the centre, a lot like what I said the Milky Way and other local galaxies do. And actually, if we compare it to the kind of model we expect for a galaxy with Milky Way-like rotation, it's a really, really good match. So this was a really exciting result for a number of reasons, and this made Rebels 25 the most distant confirmed rotating disk that we've observed so far. And also because its rotation is so ordered, it's actually the most distant Milky Way kind of look-alike, in terms of its rotation at least, galaxy that we've so far seen. And so this was surprising or baffling, if you prefer, because it really tells us a lot about how those early galaxies, so those kind of redshift 14 galaxies that are really bright, maybe it's possible that they've grown and evolved and settled into rotating disks a lot faster than we had previously thought. So this is also telling us stuff about the highest redshift galaxies that we've observed. So this was super exciting. And that is the end of my talk. So I'll leave you hopefully with a video where we zoom in to Rebels 25 and happy to take questions. It will eventually get there. Are there any questions? Yep, over there.
Could you show the residual gap?
Yeah, the residual for the rotation map. Yeah. Sorry, Karen.
Yeah.
We'll skip to the end after. Yeah, so this one, so this is the data minus the model.
So it's, I can see on the left it's quite large compared to the model.
Yeah, indeed, this blue region. So we're at very low signal to noise at this side of the galaxy, so this could just be consistent with noise. Like it's hard to look into too much detail when we've got such low signal to noise here. But yeah, like there are of course quite a lot of features within the residual map as well. But yeah, this is really just a signal to noise limitation. We can't look into too much. We can't look into too much detail in the structure of the residuals at this signal to noise.
When you detect oxygen in such a distant galaxy, does that mean that there are already a second generation stars formed?
Yes, yes. So the question was, when we detect oxygen in very distant galaxies, does this mean they're already second generation stars? And so indeed, so one of the big focuses with James Webb observations is trying to find what we call population 3 stars. These are kind of the very first stars to form within the galaxy, and we expect them to form in completely pristine environments, but there's no elements like oxygen, just very pristine elements like hydrogen and helium. So the fact that there's already oxygen in this galaxy means that there have been indeed previous episodes of star formation that have already enriched the gas within this galaxy to the point where we can detect signatures of oxygen like this. So yeah, this was a super exciting finding. Yeah.
In the first observation, you showed 3 different blobs, but they don't coincide with the rotation. Have you explained those?
Yes, okay, yeah. So for Rebels 25, if we can go to the map. Sorry, Karen. I'll skip to the answer. So what we think is happening here is these blobs, and then also if you go to where it is with the C+ with the gas. So what we think is happening here is, so the blue contours are kind of where the gas, the star-forming gas is, and then the orange contours are actually where there's dust. And what dust is really good at is absorbing blue light and then re-emitting it at red wavelengths. And these blobs are very, very blue light. So what's probably happening here is that any light that was emitted in the center is just being really strongly absorbed by the dust, because there's going to be a lot of dust at the center of this galaxy. Which was an interesting finding in itself, because dust, like oxygen and other elements, takes a long time to form. So it was quite also cool to see that there's so much dust already in this galaxy, given that it's only being observed like 700 million years after the Big Bang.
So you also have planets with oxygen. Wow!
I wouldn't go that far. Yeah.
How these findings about the oxygen in the late universe change our belief of the early history of the universe?
So when we look at how much oxygen there is in galaxies,
how all these findings about what is happening in the early universe change our picture of what happened early.
Yeah, okay. So yes, the question was, how does the detection of oxygen in the early universe change how we think galaxies evolve, essentially, yeah? So when we are looking at things like oxygen or other kind of heavier elements, we call them within galaxies, we kind of call this the metal content of galaxies. So astronomers like to make things simple, so anything heavier than helium, which is like the second lightest element in the periodic table, we call a metal. So when we look at how much oxygen, we say, how metal-rich is the galaxy? So trying to predict how metal-rich galaxies should be across cosmic time is actually pretty difficult, and there is a lot of variation between different, for example, cosmological simulations in how much they predict how metal-rich or how oxygen-rich a galaxy should be at whatever redshift. So it's a little bit difficult at the minute to fully put strong constraints on our cosmological models, just because there's so much variation in how you tweak certain parameters and what sort of prediction you get out. So it's a little bit difficult at the minute, but this is something that I'm also looking into a lot with Rebels 25, because as it's dust-rich, it's also metal-rich, and also some other galaxies that are quite similar to this one.
what do we learn from the model that you fit to the rotation curve? Does it look the rotation pattern like the nearby galaxies? Are we learning something about the dark matter and the halos and things like that?
So a bit of both. So the first, easiest constraint we make is how much rotation is there relative to turbulent or random motions. We call it the V over sigma ratio. It's just how strong is the rotation compared to the more random motion. And we also use this to constrain cosmological models, like how much do they predict galaxies should, what V over sigma should they show with redshift. So that's the first kind of quantity that we measure. So we measure V over sigma and compare it to our models. And for Rebels 25, it lies quite a bit above most models. This doesn't mean we're breaking the models, by the way. This is one galaxy, and it's a very cool galaxy, so these things can happen. The other thing we can do in terms of the rotation curves and fitting dark matter profiles, we can try to do this with this galaxy. I have attempted this. But even though I convinced you that this is really, really cool and high resolution, it's actually not quite high resolution to do that very well. But it's kind of the best we can do at the minute without something like gravitational lensing.
I do have a question. So, as my memory is, if I'm not mistaken, galaxies are, as they rotate and they evolve, they become quite flat.
Yes, exactly.
So, but here it gives the impression that you are looking on the galaxy from the side, but at the same time it has volume, so it looks quite spherical rather than a flat galaxy.
Yes, that's a really good thing to point out. So it was about what inclination could this galaxy have, essentially. So from the model that I'm showing here, this is a galaxy that's slightly inclined. So still fitting it with a pretty thin disk. From the measurements of how the gas looks, we try and get a thickness, but it's very difficult at this resolution, so we assume that it's pretty thin. We also try with a thicker disk. And so then we can also fit for the inclination. So what I find for this galaxy is that it is slightly inclined, enough to still get these rotation signatures, but it's not, so if it was fully face on, you wouldn't see this kind of velocity structure. But so it's slightly inclined, enough that we get, a rotation signature up to about 150 kilometers per second. If you then correct for the inclination, this then becomes a much higher velocity, something like 300 to 400 kilometers per second. So yes, even just a slight inclination is enough to give us this kind of velocity structure.
Yes, perhaps a bit of a question. I was wondering, so at the start you were talking about redshift and about how that's measured for relative distance. There's of course a measure first for relative motion. So to what extent do you know whether a galaxy is truly at the edge of, let's say, the galaxy, and to what extent you know that it's either some coincidence or some other reason just moving away very fast, but perhaps closer and not so far away?
So if I understand your question correctly, you mean how much could other motions affect your distance measurement? Yeah. Okay, so this is a big problem more for local observations. So for example, when we observe galaxies that are in a cluster, like the Virgo cluster, because there are so many massive things so close together, they get kind of pulled together. So if you try to measure the redshift or how fast any individual galaxy is moving away relative to us, you're going to get kind of messed up by the fact that these galaxies are moving, orbiting each other or moving towards each other as well. When you go to these kind of redshifts, those kind of velocities don't really have much of an effect. It'll all be included within the uncertainties, because it have a much smaller effect than the kind of recessional velocities that we see at high redshift. So yeah, so it's more of a problem for kind of more local observations.
I think that would have been a great final question. I'm just thank you. See you again.